Okay, hi, good afternoon. We are
Group 6.
Group 6, and we are going to do the demonstration for the Lab 4. So I'm Iman, this is Abe, so we're gonna start demonstrating our Lab 4, okay?
Yeah.
For part 1, the input port that we are using is A2, A4 and A13, while the output port will be D1, D2 and D4. So as you can see, this table here is actually the table for our input port, which is the switch. So we have port 0 to port 13, and as I mentioned just now, our input port will be A2, A4 and A13. So we will be manipulating these 3 ports in order to get the output that we want to get. So we have 6 output that we want to achieve. So output 1 to output 6, which will be used in the set LED function. So as we can see here, so in order to get LED 1 to light up, so for LED 1 we wanna set A2 equal to 1 and A4 equal to 0, A13 equal to 0. So in order to set LED 1, it will be 2 power of 2, which is 4. So as we can see from the table here is for LED 1, it will be the hexadecimal that represent LED 1 will be 4. So for the next one, when we want to light up LED 2, for the Charlieplexing to work, we have to light up we have to make A4 high, A2 low, and A13 low. So in order to achieve that, we have to go to A4 that we have to make it into 1. Hence, 2 power of 4 is equal to 16. So as we can see here, the hexadecimal to represent A4 equal to 1 is 16. And for the next example, let's say we want to achieve, we want to light up LED 6. So to light up LED 6, we have to make sure that port A13 and A4 is equal to 1, while A2 is equal to 0. So we have to take, in order to translate that into hexadecimal so that the computer recognize it, is we have to take 2 power of 13, which is 8192, plus with 2 power of 4, which is to represent port A4, which is when you take 2 power of 4 is 16. So you add up the two numbers together, which is 8192 plus with 16 is equal to 8208, as we can see from this table here. 8208 represent LED 6. So the others are the same. When we want to light up a respective ports, we just have to take 2 power of the number of that port in order to represent that into hexadecimal. So that's all for the switching part. Next, we'll be moving on to Charlieplexing. Just now we know that we have to program the number 16 in order to light up the LED 1. So the microcontroller will take inputs from the switch, which is the number 16, which can be translated into 001. So once it knows that it has to light up LED 1, it will send a signal from port D1, as we can see from this figure here. So it will send a high output to D1 and low output into D4. So besides that, it has to program port D2 into high impedance or tri-state in order to let the current flow from D1 and D4. So when the current flow from D1 to D4 and not passing through D2, it will make LED1 to light up. So we can take another example here. Let's say if we want to light up LED 6, so LED 6, we must set D4 equals to 1, which is high output, and D2 equals to 0, so that it passes through the LED 6, and we have to make port D1 into high impedance so that there is no current, so that the current choose the easiest path to flow, which is from D4 to D2. Hence, we can use this principle, this concept to make Charlieplexing to work. So that's all for part 1 on the Charlieplexing part. Next, we'll be moving on part 2. But before that, I would like to show you our output. Since there's some problem with our 4-way switch, I have to connect the input and output manually, so we cannot show it inside the video. So this is the output that we get by connecting it manually. So these are the 6 output.
For assembly function, a main function was created in assembly. Over here, as we all know that we're using port D1 to 4. So the PDDR, PSOR, PCOR, PDOR values of port D were taken from the data sheet, which was mk20ds.h, the header file. After getting that, we made a function called setLED. The type is also setLED function. Over here, what we did is that we load R1 and R2 with the PDDR and PDOR respectively. Basically, we save the PDOR into R1 and PDDR into R2. After moving on, we had another function called 0. Basically, over here, what it does is the output register, which is your R0, it compares CPM compare CMP compare R0 output register with the decimal value of 0. If branch not equal to 0, then move to the move to the branch 1. This is branch 1. And if it is equal, then move on to the next command of the branch. Okay, over here what we do is we move the value of R3 we move the 000 value into R3 and then simply give it a direction and then saved it into R3. So PDDR registers was taken and saved into R3 with the offset of 0 and then branch to end. Basically end is basically just ending the functions. Moving on to 1, the value of R0 was compared to the decimal value of 1. If the branch is not equal to 1, then move to 2. If equal, then move within the function within the branch of 1. Over here, it gets a bit complicated. What we do is we move the value of 0, 1, 2, which has got the reason. Okay, first of all, let me explain what we did here. The 0, 1, 2, the value was moved to R3. The reason of doing this, in Charlieplexing, we all know that 1 has to be set as an input, 1 has to be set as an output, and 1 is left behind. Over here, we are basically defining which one is left behind and which two are basically the outputs. Initially, we cannot go it in one line and say this is the input, this is the output, and this is supposed to be left behind. So we make these two for D1, we make these two the outputs, and this is left behind. What we do afterwards is we move R2, which is again PDDR. PDDR is moved into R3 with the offset of 0. Basically, it has been, the direction has been given, and then we move 0x2. Basically, this command is to tell which of these which of these ports are going to act as an input, and the remaining is going to be an output. So initially, we have already described that this is going to be left behind. Out of these two, which exactly are this is the one that's left behind. This and this has been set as an output. How exactly do we turn D1 on in order to turn the D1 on? So port D1 was set as an input, left behind. This was set as an output. So the flow will be like this in order to turn the D1 on. Over here, that is what has been done. 0x12, both D1 and D4 were set as output, D2 was left behind. We moved the direction R2 PDDR register into R3 with the offset of 0. Over here in 02 was defined that 02, which is basically 2 to the power of 1, port D1 is going to be set as an input. Then what we do is we move the value of R1 which is basically PDOR, giving it a direction, which is giving it an output with offset of 0 into R3. This basically turns the LED number 1 on, and then branch N moving to the next one. Over here, the same thing has been done. Compare the value of R0, the output register, to the decimal value of 2. Branch not equal to 3, move to 3. If branch not equal to 2, move to 3. If branch equal, then move within the branch. Over here, the value of 0, 1, 2, yet again, because of the fact that this and this has to set, yet again be set as an output, this has to be left behind. But in this time, what will be changed is that this will be the input and this will be the output. So the flow will be like this in order to return the D1 on. Over here, that's why 0, 1, 2 was done in order to tell that D1 and D4 are basically set as outputs, D2 is left behind, and then a direction with offset of 0 was moved in. The register, the direction register with offset of 0 was moved to, was stored in R3, and then 0, 1, 0 was given, which is basically telling which is going to be the input, and then simply giving it a PDOR to turn the LED on. The same case has been done for 3. Over here, R0 is compared to the value of 0, 3. Branch not equal to 3, move to 4. If equal, then remain within the branch. Over here, the value 0, 6 was moved into R3. 2 to the power of 1 and 2 to the power of 2, add them up is equal to 6. So these two were set as outputs, and this was left behind in order to turn D1 on. The flow is going to be like this, so this needs to be the input and this needs to be the output. And then again, with offset of 0, the PDDR resistor was stored into R3. 0, 2 was given, making it the input, making it the input, 2 to the power of 1, making it the input. So the flow is like this, and then moving R1 with offset of 0 into R3, not moving, and then to turn the LED on, and then branch N. For 4, the same thing was done like we had between D1 and D2. These will yet be outputs, but one of them, the inputs will be interchanged to make the flow in order to flow like this. So the same thing has been done. 06 R2, the PDDR register was saved into R3 with offset of 0, and this time 04 was given, which is 2 to the power of 2, making this the input, and then storing the value of R1 with offset of 0 into R3. For 5, the case changes, due to which, because this will be left behind, this will be your outputs, these two, in order to turn these two on. Over here, this will be R0, the output register is compared to 5. If branch not equal to 5, move to 6. If branch equal, then remain within the branch. Over here, the R3 was to the value 14, which is basically 2 to the power of 4, which is for 5. We compare the value of the output register R0 to the value decimal value of 0. If branch not equal to 5, then move to 6. If it equal, then keep within the branch. Over here, the same thing has been done. 0, 1, 4 has been done, which is basically telling that this time these two are set as outputs. And this one is basically set as a high impedance, so left behind. We store the value of the PDDR into R3 with offset of 0, and then 04 basically 2 to the power of 2, which is this, has been set as an input, and this flow goes like this, which turns LED 5 on. Over here to demonstrate, I have LED 5 already turned on. As Iman already mentioned that our switch is not working, so we were told to just set the LEDs in the code on the main function to turn the LEDs on to check if Charlie plexing is working or not. So over here, 5, this is LED 5. 5 is working for through our assembly code. Going on to the last one, which is 6, same thing. 0, 1, 4 was set, which is these two were set, and this time 1, 0 was put, and compare. After giving it a PDDR with offset of 0 into R3, storing it, we moved the value of 0, 1, 0 into R3, and then R1, the output was given to R3, and hence branch to end. And this is all from my part. Thank you very much.
On the 1 second delay, so we are required to make a 1 second delay in assembly function. So as you can see inside here, so this is our function 1 second delay, and this one is our delay. Okay, our delay, we set it like this. Okay, so I will explain why we set it like this. Okay, so our clock on the board is 48 megahertz. So the frequency of the clock for one cycle, you have to take 1 second divided by 48 megahertz, and you get around 21 nanosecond. So in order to run one cycle, we have in order to run one cycle, the time needed to run one cycle is around 21 nanosecond. In 1 second, it can run around 48 million cycles. So I set it for our loop. We have 3 cycles, and each cycles we have to make this one equation, and 3x plus 6 equal to 48 megahertz, and 1x we get around this number of cycles. Okay, so after we get this cycle, the number of cycles, we just input it, we just replace the delay for this value. Okay, and then for the 1 second delay, as you can see, we push it into the register, and so basically it's like this. This is our loop. We have 15998, and inside the loop is basically just minus. So from 15998, each cycle will minus 1, minus 1, minus 1 until it becomes 0, and when it becomes 0, it will exit the assembly function. So this is a very basic assembly function. So inside our main function here, I will explain on straight away part 3, which is the main function. So as you can see, we have to initialize the clock. If we don't initialize the clock, it will use the 24 megahertz instead of the 48 megahertz clock. So we have to initialize our Charlie plexing, and we have to declare the I value here as because we have 6 LED to be light up. So we have to make a for loop inside here, and the value of I will be substituted into the set LED, and the set LED we will call it from the top here. Set LED will be using assembly function, so we'll call it inside our assembly function, which is this one, the one that Abir just now explained. And after that, we will make 1 second delay. 1 second delay, we have to put an X inside it because I've been using X as the medium. So the value of X is 3 because we have 3 loops. And after that, we have delay. So when you run it, it will become like this. So we are trying to run it right now. It will run from LED 1 to LED 6, as you can see, with a 1 second delay. As you can see, our circuit is working fine. It runs through from LED 1 to LED 6. So I think that's all for part 2 and part 3. Sorry, part 2B and part 3. So thank you so much.